There we go. So yes, welcome back, folks. Happy garbage day. Lovely fall afternoon that we have here. So let's see, nothing was due yesterday, which is always nice. And in that absence, then that means that I have to put up work for you to do. So I wanted to point out a couple things on our syllabus here. So we have a homework due next Monday, which is available inside the homework portal. So you're getting a chance to do a little bit of a classical test theory stuff as well as CFA practice. So this is canned data. The objective is for you to get used to writing code and searching through the output to find all of the things, as well as processes involving likelihood ratio tests, so that you can get practice ahead of doing your own data, which is assignment 3 that has been posted here for the 24th. So relative to this assignment in years previous, I've added a lot of text related to writing. I used to give feedback after it was due, and then I thought, why don't I just tell you this stuff ahead of time? So I'm looking for you to be able to demonstrate proficiency with these skills, not necessarily looking for you to get to the land of good fit. I understand that with real data, that might not be possible. But what I'm looking for is that you understand the results of the analysis well enough to make an informed decision. Am I going to change the model? How would I change the model? Or are the suggestions that the program is giving me just ridiculous and I don't want to change the model? I'm also trying to give you practice with what should be an empirical results section of a manuscript. And so even though I have a list of items that should go into your report, I do not want a numbered list back. I want a real results section. So it should include things like transitions between paragraphs. It should reference your tables and what they say, not just make the tables. Speaking of which, I wanted to give you, in case you have not seen this before, so let me grab some M+ output real quick so I can show you something with respect to making tables. Two-factor, let's do this one. So I asked for a lot of tables of parameter estimates and things. And I wanted to make sure that for those of you who are not using R or some package where the tables are based in it, but you're having to format output, I wanted to show you this trick here. So this looks like M+ output here. This is text, so it doesn't understand that it's a table. But if I copy it and go into Excel, you make a new one here, and I paste it in, Excel doesn't yet understand that this is a table either. But I'm going to do a magical button under the data menu that is called text to columns. Have you seen this before? Okay, it's magical. So it'll ask you, okay, how would you like me to split this? And you can either say it's delimited, like for commas or spaces, but fixed width will work in this case. It then puts where it thinks the line breaks should go, and you can add them or remove them. And then if you hit finished, it puts it into a table. Yeah. So normally I'm not a big fan of, doing things by hand in terms of mousing and whatnot, but if you just need to make a table real quick, this is how you make it real quick. And one of the things that I ask for instance, is to keep the decimal values consistent. So like this one right here has fewer. That is also an easy fix. If you go up here and hit, let's see, format, in the home button, you can turn this into numbers, and then you can control the level of precision of your numbers. So relatively easy to make nice looking tables. The other last step then would be to not leave these labels here, right? This is bad. So like what could go here instead of sit by?
The name factor?
Yeah, what are these? What are these values? Like what? Yeah, so I would be like factor loadings. And I'm okay with you leaving in the item numbers. If you have room, you might refer to their content or something like that. You don't need these two columns. What you can do instead is add standardized values as your last column, like it does in Levon output. And then I have several examples of tables. So like here's what a table would look like to describe model fit. Here's tables that describe comparisons. Here's a table of what the estimates would look like. So here's the two-factor model that I landed on. I've got unstandardized columns and standardized columns. And in R, I could not find a way to get this column easily. And when I did find code to get it, the standard error for the standardized estimates did not match what they were in M+. So that one's optional. But I think having the estimate, its standard error, then if they wanted to, they could convert that into a t and get the p-values and all that, right? And then just having the estimate for the standardized column with these things clearly labeled. So examples that you can feel free to borrow in your lives. Yes, sir?
In the real world, are you kind of using asterisks to show significance?
No.
Okay, I had a feeling.
The question was, do I like stars for p-values? No. I think they're visually cluttery, and I especially don't like it when it's 1 star if it's less than 0.5, and 2 stars if it's less than 0.1. Like, no, get off the fence, right? Like, so what I tend to do is bold things that are significant, and then say in the note that bold things are significant. The end. So I don't like the clutter. By the way, for things that don't go above 1, so for like correlations and stuff, you can remove the leading zeros as a number format. So if you go into the numbers and hit more, one of the options is custom at the bottom here, and then you can like take off that leading 0 and have as many decimal places as you want. So for tables of correlations, I take off the leading zeros because you never need them. And this will also make it so that negative and positive values stay aligned if you make your tables this way. So I like Excel for this because it's nice and transparent and easy. But if you have another piece of software that makes tables nicely, Godspeed. Right? If you want to make a markdown document or whatever, Godspeed. Have fun. Just have everything look nice and neat and publishable. Because hopefully you will be able to take the results of this and use it as the basis of a publication. And a lot of students in SEM over the years I've taught this have done so. So that's my hope for you. So let me know once you read through the instructions if you have questions about what to do. Just like homework 1, this should be submitted through Icon under assignments, and then I will give you feedback by inserting comments and edits into Word. All right, and one more housekeeping thing. We are meeting on, let's see, what day is this? Here we are. We are meeting on Thursday, but a week from Thursday we are not meeting. I will be out of town at a conference leaving Wednesday and not getting back until Sunday, actually. And instead, I've left you some stuff to do. So I have a video about EFA and CFA from my previous version of this class. There's also extended lecture videos and materials under Files and Icon from a previous class that Jonathan taught where he goes into even more detail, as well as some associated readings. So if you want to know more about EFA and why I think it's a waste of time, those are some things you can work on. And you can also be working on your assignments, own data analyses while I'm gone too. Coming back then, we have a formative assessment that I'll put up before I leave, as well as optional revisions for homework 1 if you need to make them. Okay, so any questions on homework, logistics, schedule? No, okay. Then I wanted to highlight an article that I referenced at the end of last time, but this as a good transition, this one. Fernando 2009. One of the things that he did in this article, which I really, really liked, and I put into this example 4 spreadsheet. So this is the idea of predicting when the responses go out of bounds according to a CFA model. So in your homework 3, I've asked you to make pictures like this, so you can borrow my calculations and plug your own numbers in. But for instance, for the forgiveness items, the scale is from 1 to 7. And given the factor model solution, so the unstandardized intercept, the unstandardized loading, I can calculate at representative values of a factor score what the model predicted item response should be based on this CFA linear equation. And he figured out in the article, I've programmed it into Excel, the exact points at which the predictions go out of bounds. So I think in deciding whether CFA is good enough or whether you need to switch to a model that is designed for ordinal responses, which is where we are now transitioning to, this type of information is very useful. So that's where the source is for these calculations, was that 2009 article. And you'll note that I have the dashed lines programmed in here as lowest and highest. This is something then that if your scale doesn't go from 1 to 7, you can update the numbers and then you'll have your own boundaries as to where out of bounds is. Okay, So this is from the example 4 spreadsheet. That's been up for a month or so. I haven't messed with it. Has a lot of stuff in it in terms of calculations and recipes for making stuff. But today, we have a new topic to start with. Are we excited about that?
Yes.
Yes.
I've been hanging on to this since last year.
Yes, so there's some good news and there's some bad news. The good news is that models that do factor analyses for ordinal data are not that far away from models that are not for ordinal, like what we just did. The bad news is that there's just enough layers of complexity that it kind of makes your head hurt. I'm just going to put that out there. But my job is to try to make it as least painful as possible to be able to figure this out. And this is one of those things that you will see in the literature named a bunch of different ways. And so the beginning of this lecture is me trying to give you like an orientation as to what people call stuff and what they actually mean when they use those words. But the big picture is that we are transitioning from factor models that assume the responses are normally distributed and continuous into factor models for binary responses in this unit, and then extending that into ordinal and nominal. Once you can do binary, ordinal and nominal are super straightforward. Like there's just like this much further. But to get from regular to binary is a leap. If you had generalized modeling before, this will go better. If you didn't, I will recommend that you revisit that material in my earlier class, because you got to know what a logit is to get through this stuff. Did I tell you my story about logits? Maybe I did. When I first learned IRT, which was from Susan Embertson in the year 2000, and I know it was that year because that was when her book was just published, and she used to talk about how the model was linear in the logit, and that was such a good thing. And I sat there the whole semester going, what the hell's a logit? Like, I don't know what this word means. And I felt too stupid to ask, or I tried to ask and it didn't work. I still didn't get it. And I feel like had I just had that piece, it would have been so much easier. So we're going to start with words, orientation, and what the hell a logit is, so that you don't have to suffer the way that I suffered. Fair? All right. Please don't be shy about asking questions, asking me to repeat myself, or even if your question is, let me just say what I think you said and see if I'm right. Like, that's a fine question. Or if your question is, what? I can't. What? That's also a sign. So I want to be sensitive to the working memory overload that this can be, and be respectful of that. But it's also really cool and kind of fun. So one of my favorite things to talk about. With that caveat in mind, away we go. So big picture first. So let's review where we've been, since this is week 7. Not really halfway there yet, but approaching the halfway mark, maybe, give or take. So where we were first is classical test theory, which is the set of beliefs, rules, and procedures that make it okay to add items together and call that sum an estimate of a latent trait. In those models, we don't care what the item responses are because they're not part of the story. We work with the sum across items or the mean across items. Anytime that you're working with a summary of information rather than the original information, you necessarily have to assume things about the original pieces that you no longer have. And in this case, we're assuming items are exchangeable. The only way to get a better measure that's more reliable is to get more items. That's it. And alpha, as an index of measurement error, assumes unidimensionality, assumes tau equivalence, the equal loadings, and assumes there's no error correlations. Other measures of reliability assume even more things, such as Spearman-Brown, which further assumes parallel items. Do you remember what the difference is between these two? Cough, cough, homework question. Tau equivalent versus parallel?
Tau equivalent is equal, is the same difficulty?
Other word.
Discrimination.
Discrimination, yeah. So tau equivalence does not have to do with tau. It has to do with lambda, and I don't know why it's called that. But that's just the term that people use. A true score equivalent is another phrase. You can also say equal loadings, equal discrimination, items are equally useful. All of those words map onto that. That's tau equivalence. Parallel takes it one step further and says what else are equal.
Error variances.
Yeah, the error variances. Yeah, so it's parallel loadings and equal loadings and equal error variances is parallel. And so to do like the Spearman-Brown formula to say how much reliability would increase if you added more items, that's parallel items. All right. And yeah, a difficulty no one cares in these models. Doesn't matter. It's going to start mattering, but no one cares at this point. So this approach is fine if you only have 10 subjects. It's probably all you can do. But in terms of real-life measurement, this has several undesirable features to it in that everything is sample dependent. So if you have an item that, say, 80% of the sample got it right, is that because you have smart people, or was that item easy? What if you want to be able to compare scores in your sample with scores in someone else's sample, but they used a 9-item version of the test instead of 8? Can you really compare them?
We're linking.
But you didn't link. I got 2 sum scores, right? And none. I mean, you'd have to do some like verbal gymnastics to make that comparable, but no. So the problem with this idea that the latent trait is the sum score is that it ties you to the particular items given. You can't make the same types of inference about what the trait is if you don't have the exact same items. And that causes problems. So one way to break that tie then, the first thing that we saw is CFA. Now we have added to the model an explicit separate representation of what the trait should be that's not just the sum of the items. So we're switching to an item level measurement model in CFA where each item gets 3 things. What are the item measurement parameters in CFA? Remember, we did this last week. Each item gets its own ...
Loading.
Loading, that's one. Loading is discrimination. Yeah, intercept is our difficulty, except it's backwards, because higher values mean it's easier, or more endorsable, however you want to think about it. And error variance. Yeah. And the reason that we have a separate error variance for each item is because each item is supposed to be normally distributed. So in the normal distribution, that's one of the few where you have a separate mean and a separate variance, as opposed to them having to be tied together. So E is going to leave us very shortly. Because if you don't have a normal distribution, you don't have a separate potential variance. The rest of this is going to stay, but it's going to look a little funky, and we're going to change the notation. Because why would we use the same symbols to mean the same things? That's not fun. So the logic of CFA then is that if this model is right, if all of these items measure 1 factor, then I should be able to recreate the covariances among the items with the loadings on the factor. And to the extent that the loading predicted covariances match those of the original data, I'm good. To the extent that they don't, I'm wrong, and I have to go back to the drawing board, at least to some extent, in thinking about how to rearrange the model. So factors represent testable assumptions. This model in particular looks like it would be a local independence model, meaning that the y's are supposed to be related only through the f's, and the e's are unrelated. Could we let the e's be related if they need to be?
Yeah.
Sure. Should you be very careful in doing that, though? Yeah, reviewers will yell at you, and rightfully so, because if you just follow the cheat code modification indices, you can add stuff to your model that makes no sense, wouldn't be replicable, wouldn't be defendable. So very carefully adding error relationships. It's usually better to readdress the hidden dimensionality with multiple factors instead, because then at least it's a principled statement about why these things are related to each other. So items are allowed to vary in discrimination, and we can build a new reliability coefficient that takes that into account, which is omega. We can also do factor score reliability. And in terms of how you would go about making your test better, more items should still make it better, but it's more better items, were the loadings. So if you had, say, a 30-item test and you wanted to make a short form, if the basis of your measurement model is CFA, then all you would look at is the loadings, and you'd pick the 10 highest loadings and you'd be done. Now you might also want to pay attention to the content to make sure that sort of the overall, like what the factor is supposed to be about is still represented by those 10 items. But the loadings are supposed to be like the only thing that matters. We ignore difficulty. Because if the loading is steep, it's equally steep for everybody all along the point. The loading keeps working the whole way through. That's going to change after today too. So measurement error is still assumed constant, reliability is assumed constant, and those things are a consequence of this idea that this is a linear model. The way that the item response relates to the factor predictor is linearly. Now, where that can go out of bounds then is like most of the time, right? So why do people do this? Because it's easy. It's what came first. It's what's built into all the different software programs. It estimates super fast and super well. But this starts to break down to the extent that you don't really have continuous outcomes to be predicted by this linear model. So that's where we got to head to something new. So I'm drawing the parallel between a confirmatory factor model and linear regression quite directly because they do the same thing. The only difference is what kind of predictor variable you have. It's called a general linear model or just linear regression if you have an observed predictor, whereas we have a latent imaginary predictor, which itself would have to be estimated after the fact, and that's confirmatory factor analysis. So the same exact tie between observed and latent holds in what we're about to do. So if you understand how these generalized regression models work, a logistic regression for binary outcomes, or a probit regression for binary outcomes, what's known as multinomial, which often goes with nominal, but not always, those models are directly equivalent to what we are going to talk about as item response theory and item factor analysis. It is the same. So the place where I finally figured out what a logit was, by the way, was in 2004 or 5 when I was a postdoc, and I was auditing a class at Penn State where they were discussing logistic regression, and I was like, oh, holy shit, I finally get it 5 years later, because it is the same thing. The reason that I was so confused, though, is that it does not look the same at all. Like, it's two completely different ways of representing the same thing, and that's what makes it confusing, because visually it's very, very different, but it is the same. So the idea then is that we're going to be changing two things about our CFA model to make this work. The first thing is that we can't predict the item response directly, or it will go out of bounds. So we're going to predict it indirectly through what's known as a link transformation. The second is that for outcomes that are bounded, the residual variance can't be one number that's assumed to be constant. It has to change as a function of the mean, because predicted outcomes that are very close to the boundary necessarily can't have as much variance around them because you're up against the wall. So we don't have a residual variance that's one number anymore. We may not have any numbers at all. So we switch out the distribution that goes with the responses, and we switch out how we predict the outcome. And that gets us over into this square. And yes, if all of this is like, wah, 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 I've never heard these words before, please go back and watch some videos while I'm at my conference next week, because that will make your lives easier. So what I'm going to do is sort of like the highlights of that, but it's hard to get the complexity at the level that you need it with just the highlights. But if you know this, then this is not that far away. Okay. So here are the three pieces then that work into a generalized model. So that ized has a very specific meaning. General, as a word, has a very specific meaning. It's the opposite of general. If you say, I know, seriously, like who thought of this? A general linear model was called general because it was a generalization of continuous predictors in regression and categorical predictors in ANOVA, and in like 1940 or something, someone figured out that they all are the same thing, and so they published the general linear model. And that held for like 10 seconds until someone else is like, what about all this other stuff? And so now the general model is a very specific case of a generalized model, where general means normal distribution. Conditionally normal is what general means. It's very specific, because that's the common thread that underlies linear regression in ANOVA, is a conditional normal distribution. So I's means some kind of not normal. And it turns out that there are models built for all different kinds of not normal outcomes. You don't have to transform your data to make it behave as if it's normal, and that may not even be possible for certain things. The ones that I'm going to focus on in this class are for binary, ordinal, and nominal, so the world of categorical. But in theory, all of these models are extendable into counts, bimodal distributions via beta, negative binomial skewed counts, zero inflated things. Like, if there's a distribution for it, you can make it. You can make this work. But we're sticking with the world of categorical. So the three pieces then that go into the model, the middle part is the same. So the linear model, at the core of it, is going to be essentially the same thing as intercept plus loading times f. Like, that part will be the same. The wrapper around it is what changes. So we're going to pick up something that's called a link function, which is a transformation of the model predicted outcome that makes it so that it can't go out of bounds. In the general linear model, the link function that is applied is what's known as an identity link, which means times 1. There is no transformation. In the models that we're going to look at, there are two, logit and probit. I'll introduce what those words mean today. Probit is ogive, by the way, for those of you who've had the IRT class before. Yeah, so in this unit, rather than talking about what's going on in longitudinal, I'll be making connections to what happened in other people's measurement classes. So trying to keep the linkages alive. So the link function makes it so that our regular linear model predicts this transformed version that when you reel it back in, stays within the bounds that it's supposed to. The conditional distribution then has to do with what values the outcome could possibly be. So if you have a binary outcome, so I think, Kaylin, you have binary outcomes, right? It's like whether or not this happened to you. So binary, not great for sensitivity, right? Because whether or not is not a very fine-grained distinction, but it is a question people could answer real quick. So you might have time for more items than if they were more complex. Well, in that case, your residuals can only be like how far off of 0 or how far off of 1. Like they can't be normal and they can't have constant variance. But it turns out there is a distribution that's built for binary outcomes. It's our friend Bernoulli. There is a distribution that's built for ordinal or nominal outcomes. That's called multinomial. So we just switch what we're assuming about the shape and the sample space of the outcomes to make something that's going to be more appropriate. And then we change the way that we compute height to use that distribution instead. So rather than height as given by the normal distribution, it's height as given by Bernoulli or multinomial or whatever. Each of these distributions has a formula for height. Okay, so here's how this works for binary, because if you get binary, you're home free. Honestly, the others are just like this much further than binary. And I know you're laughing at me like I don't believe you. Like, no, but binary it's the core of this. So this is why we do binary first. So let's say that I don't know any of this, and I'm like, I'm just going to fit a regression model predicting my binary outcome like normal. See? There's a pun. Like normal. Ba-doom-shh. Like normal. Yeah, I know. Tough crowd. With my general linear model that looks like this. So the conditional mean that I'm trying to predict then, the mean of a binary variable, is the proportion of the people who have a 1 instead of a 0. It will always be a 1 in this class. It switches depending on your software otherwise. But like if you don't know anything else about a person, what's your best guess as for their outcome? It's like, well, how many people got a 1? Like, okay, I'll give you a 0.6 probability that you get a 1 because that's the mean of the variable. So if I start with that as an idea, then what I'm predicting is the probability of a 1, and I can throw a linear model on that. So beta 0 would be the expected probability of a 1 when my predictors are 0. Beta 1 would tell me the change in that expected probability of a 1 for a 1-unit change in x1. Same thing with beta 2. And E would be the discrepancy. So what could possibly go wrong? Well, first off is the idea that slopes keep going. So the previous linear model has linear slopes in it. So it would be something like this. So I'd have my x predictor. I could have my beta 1 slope, and if the slope itself is 1, that's how I made this picture on the left. And at high values of x, if the slope keeps going long enough, what happens?
Out of bounds.
Yeah, so like if 1 is like, let's say, a passing grade and 0 is failure, what is a 1.4? Like super smart? Like you passed a lot? Yeah. And like what's a negative 0.2?
Super bad.
Like you really failed. You didn't just fail, you really failed. But no, that doesn't make any sense. What we need to do is be like, hey, linear model, can you like bend a little bit and so that way it doesn't go out of bounds? So as x goes up, you understand that you can't go past this line and you can't go past this line. Like when I run through my neighborhood, all of the dogs now have these invisible fences, right? And sometimes they have a sign in the yard that says that, but if they don't have that sign and I see the dog just sitting there, I'm like, okay, I'm going to cross the street now because I don't know if you're going to stay within bounds. And I have been bitten by a dog while running before, and that was not fun. It was a little like yip, 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 yip dog. It just like attached itself to my ankle, and I was like, ugh, get off of me. But you should have stayed in bounds, is what I would have said, right? Because I don't run through your front yard. You shouldn't be biting my ankle in the street. But anyway, I don't know if the slope is going to stay in bounds, but we have to tell it to. Otherwise, it doesn't know it's supposed to. So we need the electric fence. How's that? That's a new one for me. We need the electric fence. So here's how we get the electric fence. A transformation, not of the data. It is a transformation of what the model is trying to predict. The model predicted conditional mean, meaning the prediction is conditional on the rest of the predictors. So here's the logic of this. Rather than predicting probability directly, we can first transform it into a quantity that is known as odds. I hate odds. The good news is that odds do not have a place in measurement models. They get skipped, which makes me very happy. But they have this intermediate place in describing how the link function works. Not to be confused with an odds ratio, which is another word, because this looks an awful lot like a ratio to me, but this is not an odds ratio. An odds ratio is a ratio of multiple sets of odds, so there's like 4 of them. This is just an odds. Odds is the probability of a 1 divided by the probability of a 0. So if you have a 50-50 probability, what are your odds?
1.
1. So like neutral in odds is 1. Neutral in probability is 0.5. So here's an example of why I hate odds. So let's say the probability of a 1 is 0.7. Okay, so 0.7 divided by 0.3 is 2.33. Is that a lot? I don't know. It's positive. It's above 1, so I know that that means that a 1 is more likely than a 0. But if I go the other way, if I try to predict the odds of a 0, then it's 0.3 divided by 0.7, and I get this number, which is somehow the same. Like it's telling me the same information, but not really. So the problem with odds is that like every positive result is somewhere between 1 and positive infinity. And every negative result is sandwiched between 0 and 1. That's why I hate odds. But fortunately for me, we're not done yet. Some genius figured out that if you take the natural log of this odds, then you get something that is symmetric about 0 and beautiful. So this is our new best friend for like the next month, probably. I call this a logit. It is also known as log odds, but it is the natural log of the odds of a probability of a 1. That is what a logit is. I say logit. I once had a student say that it's logit because you don't take the log, you take the log. Okay, I'll buy that. So, yeah.
Phonology doesn't, if you have a vowel that, anyway, I'm not going to get into that. But logit, I think, phonetically makes more sense.
I always say logit. Log odds is acceptable as well. The log odds is a transformation in probability that changes it from being bounded between 0 and 1 to being completely unbounded and symmetric about 0.5. So here's what it looks like if you plot probabilities on the y-axis against what the logit would be from using this formula on the x-axis. So a probability of 0.5 corresponds to an odds of 1, which corresponds to a logit of 0. So neutral in logit space is 0. Neutral in odds is 1. Neutral in probability is 0.5. So part of the reason why IRT models, as we will see, look very different is because they're written in probabilities rather than in logits. So if I go up from 0.5 to 0.9 in probability, a probability of 0.9 corresponds to a logit of 2.2. If I go down by an equal amount in probability, that corresponds to a logit of negative 2.2. So if it's a probability of 0.99, it's a logit of 4.6, and I have, can you guess what the corresponding logit would be for 0.01? Say it with me? Yeah, negative 4.6 is beautiful. So I don't know what the hell a logit is exactly, but I do know that it's telling me the same thing regardless of how I phrase it. So this idea that you can take the result from a probability of 1 and multiply that result by -1 and get to what it would be for a probability of 0, that's going to show up in these models, that concept. Because some of the models are phrased to describe how to get to a probability of 1, and some of the model parameters describe how to get to a probability of 0 instead. But -1 gets you back and forth so long as you're in logit land. Once we have logit land, then we can predict with our regular linear slope and keep going forever and ever and ever and ever, because when you back translate logits into probabilities, you will never hit their boundaries. So you can have a logit of -6 million, and it's just above 0. That's what a logit of -6 million is. It can go on forever and ever. So here is a mapping then that I stole from a multi-level modeling textbook. This is their generalized chapter in Snyder's and Bosker, of what it looks like if you map logits to probabilities in a different way. And one of the consequences of the model being phrased in logits is that the difference between logits is not the same as the difference between probabilities. So a 1-unit change in a logit is like what the slope will predict. So like a factor loading will be the change in the logit response for a 1-unit change in the factor. So logits can keep going and going and going, but that distance is not equal in terms of probability. It gets compressed. So what happens is that the same slope looks like it's less useful the further you get towards the boundaries. It's a nonlinear relationship. So we have probability of a 1 translated into odds, which makes it 1 is the reference rather than 0.5, translated into logits, where the reference is 0. Okay, how are we doing? So big picture, what logits are doing is giving us a new outcome for our regular old linear model to predict that when you back translate into probability, the probabilities stay where they need to be, between 0 and 1. By the way, back translate, you will also hear me say to unlogit it. The proper term for that is an inverse link function, by the way. So to go from probability into logits is the link. To go backwards is the inverse link. The way that I think about this is, you know those devices at stores where you can figure out how much something costs? Yes, like if you shop at Kohl's, for instance, I've talked about my love of Kohl's many times. If you pay full price at Kohl's, you are doing it wrong. Okay, there's just no reason for that to ever happen to you, because everything is always on sale, and there's usually a coupon. Like if you return something from Amazon at Kohl's, they give you money to spend in the store. And I'm not going to let $5 go. Like I can find something for $5, so I'm wandering around the store, like trying to figure out how much real money something would cost. I take the paper of the receipt for how much, like price tag, that's the word I want. Now you see why I don't have any more caffeine. I'm already like full right on top here. I can't find with any words. I take the price tag and I stick it in the inverse logit link function, beep, and I find out how many actual dollars it is. Because the price tags are all in Logits at Kohl's. It's not actually how much you pay, because you haven't applied any of the discounts yet. So inverse link is to go from this logit unbounded thing back into probability that we know what to do with. Okay, so that only solves one of the problems. The idea of a logit solves the problem that our predicted outcome needs to stay within bounds, but it does not solve the part about residuals can't be normal with constant variance. That's why we need to switch to a different conditional distribution. So in our linear model, E is always the difference between what you actually have as y and what the model says you should have as y hat. So if y is 0 or 1, E can only have two different possible numbers. Either you're off from 0 by this much, or you're off from 1 by that much. That's it. So two possible values at each prediction can't possibly create a variance across all of these that has a shape that has a normal distribution with constancy. More directly, the way that you compute the variance of a binary variable is the mean times 1 minus the mean. So a binary variable only has maximum variance if it's split 50-50, and it shrinks as you get close to the boundaries. So we don't have anymore an estimated residual variance per item, because we can't. It is determined by the mean. Once we know what the model predicts our probability of a 1 to be, we're done. We know the error around it. It has to be whatever number corresponds to that predicted probability. So we don't have E anymore. So in our item response models, each item is only going to have usually 2 parameters instead of 3. Something for discrimination and something for difficulty or location. But error variance is not going to be part of the story anymore. So rather than saying our errors are normal, we say no, they're Bernoulli. And in contrast to the normal distribution, which has 2 parameters, the Bernoulli distribution has 1. And this is the simplest PDF probability density function I think that there is. What it boils down to is your number at the end of the function is the probability of a 1 if that's what you got, or it's the probability of a 0 if that's what you got. The end. I had to steal this picture from Wikipedia too. Let me come back here. So if I know that 75% of my sample had a 0, I know how many people had a 1. Like I don't have to try and compute the variance around the mean. I know what it has to be. So we're switching from this idea for what the E's should be to this idea, which means the E is not in the equation anymore. So it's not that we're saying the equation is perfect, it's just that we don't have this extra parameter that E was supposed to have represented. We don't have to estimate anything else. Okay, so here is the same model 4 ways. The difference is what's on the left-hand side. So my personal preference is the top one. So rather than predicting the probability of a 1 directly, we are taking the probability of a 1 and dividing it by the probability of a 0, and then taking the natural log of that. Odds is the part in brackets here. So this is logit, log odds. Once we do that, the interpretation of all of our fixed effects in our regression model here is exactly the same. The only catch is that rather than saying expected outcome, we say expected logit outcome. So beta 0 is the expected logit when x1 and x2 are 0. Beta 1 is the slope for how the expected logit changes per unit x1. And as long as you're in expected logit, you're good. So I like this one the best because the parameters then mean what I'm used to them meaning. Where this goes off the rails, though, is trying to explain to somebody what this left-hand side is. Well, you have a predicted logit of 1.4. Is that good? Well, what can you tell me about a logit of 1.4? Seriously, this is a question. What do you know if it's a logit of 1.4? At a minimum, what do you know?
It's greater than 0.5?
Yeah, so because it's a positive number, that means this person is more likely to have a 1 than a 0. How likely? Somewhere in the 70s, maybe? And I only know that through practice, right? Like, no one has the conversion of logits to probabilities memorized, I don't think. At least I've never tried. So where this breaks down then in terms of providing a prediction is what to do with this logit part. Another way to say this is, okay, well, let's take the log off of this thing, which requires us to exponentiate the right-hand side. So e to the model is what this says. This is the one that I hate the most, because then they become multiplied together, and I just can't handle that. But for this class, I get to skip this one. There's never odds in measurement models, thank goodness. So what you will see instead of odds as this middle layer is probability. So e to the model over 1 plus e to the model is how you get a predicted probability directly. And so this idea of e to the prediction over 1 plus e to the prediction, this is my inverse link function. How do I get out of logits, which is the core of this thing here, back into probabilities? And if you want to save yourself some typing, the bottom version is equivalent. The difference is in the -1 right here. That replaces the entire numerator. So when I type out formulas, I tend to write this one because it's shorter and less likely to be screwed up. So it's 1 over 1 plus e to the not logit, is the way I say that. But this is something that you probably should just commit to memory. To get from logits to probability, it's e to the prediction over 1 plus e to the prediction. Will you ever need to take a test in which you have to spit this out, though? In my class? No. But it will make your life easier if you have this just sort of stored. But you will find this in spreadsheets, you'll find this in programs, it will do the math for you. But this is how you get back and forth. So in this version of the model, the left-hand side is very understandable. Like if I told my mom, oh, you have a probability of this of 0.3, I think she'd have a sense of what that means. If I told her you have a logit of 1.4, there's no chance. But then it's like, what do I do with my slope? Any kind of language that's like, well, this is the change in the something for 1 unit, no. Like those words just don't work to describe this. So in practice, interpreting the parameters is easiest if they're predicting a logit, but then describing to folks what that prediction actually means is much easier if it's a predicted probability. So you got to be able to go back and forth. So one of the reasons why the models that we're going to work on in this unit look very different is that the world of what is known as item response models, or IRT, are usually written in predicted probabilities, whereas the world of item factor analysis, which comes out of the CFA tradition, is usually written in terms of predicted logits or probits. So this version versus that version is one reason why these things look different. Okay, what's next? Cautionary tale is next. So this is less relevant for our purposes, but I include it because I see this getting screwed up, and when people are first getting used to these models, is what you can convert and what you can't. So if you're starting with predicting logits, here are the parameters that we have. We have y hat as the result of the model. Beta 1 and beta 2 are the slopes here. If you want to go one step down from predicted log odds just to odds, then it's e to the predicted logit gives you your predicted odds, and e to the slope gives you what's known as an odds ratio. That is an effect size. So when you run a logistic regression, you will probably get a column that has slopes and logits, and then another column that has e to the slope, and that's in odds ratios. Now, if you want to go one step further and talk about it in probabilities, this is where people screw this up. You cannot take a slope and unlogit it all the way back down to probability. It doesn't work. Because a 1 unit change in logit is not a 1 unit change in probability at all points. The probabilities have to have fewer changes as you get closer to the boundaries. So that's this picture right here. So a 1 unit change in logit does not correspond to the same changes in probabilities. You cannot unlogit a slope all the way down into probability. What you can do, though, is unlogit the predicted outcome created by the slopes. So you can take a predicted logit and take that down into an odds and take that down into a probability. So we will work with what the model says the outcome should be across these different scales, but not the parameters themselves. All right. 254. How are we doing so far? Okay, so big picture. What is the problem we're trying to solve?
Boundaries?
Boundaries. So if I have binary items, I can't fit a CFA to that. One reason is that the factor loading is going to predict probabilities that go out of bounds. The other problem is that the e's are not supposed to be normal with constant variance. So logits fix the boundaries. E not having constant variance is fixed by changing the distribution from normal to Bernoulli. Now, if that were the end of the story, this lecture wouldn't need to be 90 slides. No. So you will also see, in addition to all of the other ways I've described the same idea, here's another one. The idea of a latent response formulation. So this is terminology that's used in the M+ documentation. It's used in a few different generalized modeling textbooks. This idea of Y star. Y star is in logits or probits. It is not a new separate thing. But when you're working in logits or probits, as soon to be introduced, then you have E back, because this is like the latent version of it that has some error to it, but when you back translate it into probability, the error is gone. It's constant. It doesn't need to be estimated. So in this version of it, you will see a threshold as a parameter, in which what we would say is that no. So Kaylin, I know you got binary items, but what if I told you that secretly underlying each of these binary items was a continuous variable just waiting to be discovered? Doesn't that sound nicer? So you have this continuous variable. It has one of these shapes. It has a logistic distribution, and it's in its heart, in its underlying core. And what we did is we just screwed up. We just took this continuous thing and we just chopped it in half. And you get a 1 if you're above some threshold or a 0 otherwise. But wouldn't it be nice if we could work with the pretend underlying distribution that secretly is there but you don't have? I don't know how to answer that. Yeah, exactly. So, okay, if you want to say it that way, fine. That doesn't change the fact that you don't have access to this secret underlying distribution. So we don't know if the shape is right because this is an imaginary concept. But if you're willing to subscribe to this, okay, sure, if I agree to this logic, what am I getting? Well, you get a number for what your residual variance is supposed to be. Because in this distribution, residual variance is pi squared over 3. Okay. That helps me in some contexts. So think about, let's say, standardized slopes. We use standardized factor loadings in CFA, right? What do we use standardized factor loadings for? What do they tell us?
The outcome variance accounted for our factor score?
That's R squared. I'll accept that as an answer.
Okay.
But more directly, what do standardized slopes allow us to do in evaluating our items and how good they are?
Compare items that are not on the same scale.
Yeah, it puts them on the same scale, and then we can say, well, this standardized loading is 0.7, and this one's only 0.6, so 0.7 wins. Now what do we, and then if you square it, you get the r square attributable to the factor. Now what do we have to know, though, to standardize something?
The, wow, my brain is gone. The variance.
Yeah, the total variance, right? So if you have, say, a normally distributed item response, you can say, what is its total variance? Okay, I'm going to turn that into 1 and I'm good to go. What if I have this, though? You don't have total variance. So this gimmick of saying, well, what if we just said total variance is 3.29? That gives us a way to make standardized coefficients now, because we have a scale. If you're willing to believe that your pretend underlying continuous variable has a logistic distribution, then you can say that variance is 3.29. And then that allows you to make standardized coefficients in the same way that we're used to if we have a total variance to start from. And what if someone else says, nuh-uh, I think your pretend continuous underlying distribution is normal? Okay, sure. That's probe it. That's another one. So another way of solving the same problem, that our predicted probabilities will go out of bounds on a linear model, is a different link function that's known as a probit. So we have our friend Logit first. This is a new friend, probit. Probit harkens back to my version of intro stat as an undergrad, and potentially some of yours, depending on how long ago that was. In the back of every undergraduate intro stat textbook, there's a bunch of tables. Do you remember the tables? Like Z tables, where you have like Z scores and then there's p-values in the middle of the table, or vice versa, and like critical values for chi-squares and t's and shit like that, all that stuff. So probit is going into the Z to p table and saying, okay, so the p, let's say that I have a probability of 0.87. What's the z-score that goes with the probability of 0.87 if that is the area to the left? It would be a z of like 2 and some odd, I think. I don't have those tables memorized either, but that's a probit. The idea is that we're using a standard normal distribution and figuring out what the x value would be on, like if you plotted it, what the z-score is that corresponds to that probability for the area to the left. So if you have a probability of 50-50, what does that correspond to as a z-score?
0.
0, yeah. And so within like 1 standard deviation on either side is like 67% of the data, and within 2 standard deviations is 95%. And remember the z value that you use for significance testing?
1.96.
1.96. That corresponds to 97.5% to the left, right? That's what this is. That's probit. So probit says, all right, well, I'll just convert your probabilities into z-scores, and we'll do it that way. So the motivation for this is, rather than having my pretend continuous underlying distribution be logistic, like this, let's say that it's normal, like that. So I'm on slide 16 here. I stole this slide a long time ago, and I think I stole it from Don Hedeker, but I couldn't find the source. So there's my attribution. The difference is in the scale of the underlying distribution for the binary response that we actually do have. And if you say, no, that pretend underlying distribution is normal, where normal has a variance of 1, then we use the probit, and we would predict the z-score that goes with the probability. No, I think it should be an underlying logistic distribution which has a variance of 3.29 instead. Okay, since it's imaginary, I'm not sure how I'm going to say either one is right, and it turns out that I don't have to, because some other genius figured out that if you take the predictions from these models and scale them by 1.7, the z-score that is predicted by this equation, if you multiply it by approximately 1.7, you get the predicted logit. And you go back and forth. So do you see the difference between the red line and the black line? I don't. Like, just that much. So yeah, logit versus probit, you're going to get to the same place. Probit came first. Probit is harder because there's no easy formula. Remember how to get out of logits back to probability? E to the model over 1 plus e to the model. There's none of that in probit. In probit, you'd have to integrate to figure out what the probability is that corresponds to that area. And that's why the people who made the intro stat textbooks were like, yeah, I know that's not going to happen, so let me just give you a table. So there's no easy way to get back to probability in probits. There's no odds ratios because it's not based on odds. Now, why would I even bother to teach this to you? Because for certain combinations of models, you don't get a choice. You're stuck in probit. That's why. So probit is known as ogive in item response theory world. It is the only option for confirmatory factor type models that are using what's known as limited information estimation. We will talk in greater detail about what that means, but briefly, limited information, it means that you are using a summary of the data first, then estimating the model parameters using the summary rather than the original responses. It makes it a lot easier and faster for categorical data to do it that way. So that's why we have to talk about probit at all. But just know that they're just on a different scale of what the pretend underlying continuous distribution is supposed to be. In the generalized class, I note that there are other options for link functions for binary data that assume a curve that is not symmetric. So there are models where like the top curve looks like this and then the bottom curve just kind of like peters out like this, or vice versa, like the top kind of peters out. Those are known as log-log and complementary log-log, and I still don't remember which is which, but that's not really a thing in these models. I will never remember. I've tried, and I can't. But one's log-log and the other's complementary log-log, because presumably that one was nicer. I don't know. All right. So why am I telling you all of this? You might be asking yourself. So we're fitting factor models that use logits and probits. That's why I'm telling you all of this. So item response theory and item factor analysis are two different names for basically the same set of ideas. Where they are the same as CFA is that the model predicts each individual item response. So we're not using sum scores or anything else where we have to make assumptions. We have actual predicted item responses. And each item is going to have its own characteristics, things that are close to intercepts and slopes, not errors though. And each person is going to have latent traits as predictors. So latent traits used to be F for factor. From now on, they're theta. Why? Because once upon a time, the people who made these models picked that letter, and everyone else just fell in line. It's one of the few things that people agree on in notation. It's theta. Have you ever heard anything else besides this for a latent trait in an IRT context? I've never seen it. It's theta. So it's this one right here. So it's F has left the building. It's theta now, but it's the same thing. So like the CFA models we just finished, the idea is that the latent trait theta is supposed to be predicting why the responses were related. So the pattern of covariance among the items represents a testable hypothesis. A single factor model, or a unidimensional model as it's called in IRT, would say that the item responses are supposed to be uncorrelated after you fit your theta. Theta is the reason they were related. If you have to add more than one factor, that is called a multidimensional model, which is a distinction that CFA doesn't make. Like CFA models, it's like, how many factors do you have? 1, 2, 3, it's still called CFA. Not here. It's IRT, which is unidimensional in the way people talk about it, or multidimensional IRT. But no, the rules are the same. You can have as many traits as it takes. It's a lot harder to estimate multiple traits, but that doesn't mean you can't have them. And just as in CFA, we need to find ways of accounting for unintended multidimensionality. So negatively worded items being more correlated, for instance, items that have very common specific content being more correlated, or what's known as a testlet in the educational testing literature. Have you heard this term before, maybe? Like if you have, if you say, okay, everybody read this 2 paragraphs, now answer 5 questions about what you just read. If somebody doesn't understand the paragraph, they're going to tank all 5 questions. So that introduces a dependency. Those 5 questions have a reason to be related beyond just the person's latent trait. It is specific to the paragraph that the questions are about. So that's another type of variance or covariance that has to be added to the model. So basically what it would be like is the trait predicts the common variance for those questions, and then that layer level predicts the specific answers. There's multiple ways to do it, but that's the term that gets used in this context. It turns out that error covariances are not a thing if you're using regular flavor maximum likelihood. It's not possible. They are a thing if you're using limited information estimation. So only sometimes is that a choice. And that is why factor-based solutions for dealing with error covariances are much more common. It's because they historically weren't a choice that you could even have. So how the models then differ is link functions. So IRT and IFA are to logistic or probit regression instead of linear regression, and what we call the factor. It's theta now. So the relationship in CFA models for binary responses between the response and the trait is nonlinear because of this transformation S-shaped curve thingy, which is what we need to keep the responses from going out of bounds. But that also then changes how we think about what makes an item good or not. That's the tricky part. So this same idea then, same pictures, different story attached to them. So by predicting the logit of the probability, I can have a linear slope for the effective theta. So a slope of 1, for instance, like if I had a factor loading of theta predicting my response. The relationship between my latent trait on the x-axis and the predicted item response in logits on the y-axis is linear. So Lisa, 22 years ago, are you listening? This is what linear in the logit means. It's this. It's the idea that the relationship between the trait and the logit response is linear. That if I back translate logits into probabilities, so e to the y-axis divided by 1 plus e to the y-axis, this is what I get instead. So if this was an item prediction, if this described how well this item related to theta, this has implications for whom this item is useful. Yeah. So it's going to be basically where this curve is the steepest is where we say the item is located. I'm being vague because I haven't introduced the terms yet. But conceptually, you can see that like if you're somebody who has sort of average ability, people among relatively average levels, the more theta you have, that's going to directly translate into a higher probability of getting this item response, this item correct, or endorsing this item, however you want to say it. But what about amongst people who are not super great? Like there's not much change in the predicted probability for super low people or for super high people. So the consequence of applying this boundary fix is that not all items are equally good. It's good for whom is what you got to ask. Because the slopes are going to shut off at different points along this theta distribution. So this is a good item for medium people. It's not a good item for high or low people. All of the models that I'm going to present this semester, by the way, use this same S shape. Ones that try to make the function look like something else are what's known as non-parametric IRT models. So if you want to learn about those, go ask the Google. But this is still parametric. It's nonlinear, but it's a particular flavor of nonlinear. Not just like whatever nonlinear. Question?
What does the word parametric mean?
Follows a function
Okay.
is the way I think of it. Like it's not just nonlinear, like it can be whatever it wants, but no, this S-shaped kind of nonlinear specifically it's like parametric.
Okay.
As opposed to either non-parametric or more recently semi-parametric models that try to like let the data figure out what the shape should be, and you can get kind of all kinds of crazy bendy with that. So this is not crazy bendy. This is a very prescriptive flavor of bendy that we are having in our parametric IRT models. All right. So then here's where the vocabulary comes in, and this is a good place for us to land on, I think. Yes. So the combination of how the model is phrased and how the model is estimated is what creates the vocabulary terminology. So there are two different versions I'm going to show you in terms of what the model parameters are. One is discrimination difficulty, and if you use that version of the model and you use full information maximum likelihood, that is what's called IRT. The other way of writing the same model, which is mathematically equivalent reviewer 3 of the current manuscript that I'm fighting about, not exaggerating, had to break out the no, math don't care. This is one of the few instances in which the word prove is applicable. You can prove that you can rearrange this model to get to a different way of saying it, and a loadings and a threshold, which is a lot closer to CFA. And if you do that, but you pair it with limited information estimation, that's item factor analysis. And the other cells are possible but don't have names. So that's why we're doing both of these, because I want you to understand all of these different parameterizations well enough to figure out what your software happens to be doing. That's the tricky part. It's like, what do I have here? So that's the fun we shall have over the next month, but not today because we're out of time. All right. Any very quick questions before we call it a day? Very quick?
Yes.
Okay.
If we're talking about IRT terminology, which models line up with parallel items versus tau
Both.
equivalent? Okay.
Both. Parallel and tau equivalent would be equal discriminations or equal loadings.
Okay. So it's the same thing, just expressed.
Yep, different words.
Flipped. Okay.
Yep. All right. I will see everybody Thursday. Thank you for being here. Bye, Zoomers.